Bene, buon pomeriggio a tutti, benvenuti a questo colloquium. Adesso passo all'inglese perché la nostra ospite parla qualche parola di italiano, ma quando si parla di fisica si parla in inglese. So it's a great pleasure to have here Professor Koch. She's a full professor in theoretical physics at the Free University of Berlin, and she's an expert in molecular physics and quantum control. And she graduated in Berlin, but not in Freie Universität Berlin. It was Humboldt University, right? I'm correct. And then she did her PhD always in Germany, but in another university in Berlin, right?
At the Max Planck Institute.
Then she moved for a PhD, no, for the postdoc. She moved to Saclay and then to the Hebrew, no, it's the Jerusalem University, Hebrew University in Jerusalem. And then she came back in Germany for professorship, and their research field, as I said, are molecular physics and quantum information later on. And we're really glad to have her here. Last but not least, because she's one of the Women for Quantum promoters. This is an initiative which came up with a manifesto, Quantum Manifesto of Values, which is signed by more than 200 physicists, colleagues, and female colleagues so far working in quantum information. And we really believe, I also signed it, it's an important part of our activity to take into account and to take care of gender issues, and in particular, the one related to women in quantum. And the other reason why I'm particularly glad that she's here is that she came with the funding by the University of Catania, so she's in a sabbatical here, and she will spend here 2 months, also thanks to the support by University of Catania, and I like her for this. Thank you.
Thank you very much, Elisabetta, for the warm welcome, and thanks to all of you for coming here. So as Elisabetta already mentioned, I have 2 personalities, and those who were in Modica last September saw the other personality, and those who haven't been to Modica have a chance to see the other side in a couple of lectures that are scheduled now, I think 2 weeks from now. So the quantum information part will have to wait until then, and today I will exclusively speak about molecular physics because I thought this can be of a broader interest. So quantum effects in cold and controlled molecular dynamics is the title that made you all come here. And let's start with what do I mean to that? And I really want to go to the very basics that everybody of you has been seeing at some point. And that is, what do we mean by quantum? What is quantum about? And at the very bottom, it's the wave nature of matter or wave-particle duality. Okay. And then, what are quantum effects, right? So quantum effects are effects which are related to that. So anything due to the quantum superposition principle. And my group is called Quantum Dynamics and Control. So this is the logo that my students came up with. And what you see here is a superposition of the Berlin TV tower that we thought we can maybe create with some shaped field. So that would be control. But again, this is not the main focus of the talk today. So what can be quantum effects? Okay, so interference. And if we think of molecules, what is important is to clarify to oneself that what interferes is a molecule with itself. And this is now done in experiments with where molecules are sent through a grating, for example, and you see just like the double slit Gedanken experiment, but with real molecules. So this is things that are done in the lab. Selection rules are another instantiation of the superposition principle. And of course, all the non-classical correlations, including quantum statistics and entanglement and so on. So all of this can be traced back to the superposition principle. Now, how can we observe them? Well, of course, we need sufficient quantum coherence. And if we move away a little bit from quantum technologies, where we believe that we can engineer the coherence and think of maybe more natural physical systems, then what are conditions where you can hope to see quantum effects? Well, either you go very low in temperature and you freeze out energy and go to energy scales which are relevant for quantum, or you go to very short time scales where you can also hope to see quantum effects. So the talk will be split into two parts, and I will start with very low temperature, and that's the field of cold collisions, and I'll explain what I mean by cold collisions. And then in the second and shorter part of the talk, I will also speak a little bit about ultra-fast processes. Okay, so cold collisions and what can be quantum about the collision. Okay, so here's our typical picture when we think of collision. So we have a particle colliding off some other particle or potential, and then classically these would be balls bouncing off each other. But now we have matter waves. Okay, so you can have typical wave properties, diffraction and interference. But you can also have more. So tunneling is another instantiation of quantum mechanics. And the tunneling can lead to resonances that are a signature of quantum mechanics. And the internal quantum structure, like the quantized energy levels that atoms or molecules have, can also come into play. Okay, but if you're not interested in quantum effects per se, or you find this a bit abstract, then why would you bother about collisions in the first place? Okay. Things collide all the time. And maybe you have lived yourself one of these two things, or maybe you studied physics because of high energy physics, where particles collide. And why are we interested in collisions? Well, because the collisions tell us something about interactions. And in the end, physics is about understanding interactions. Okay. And of course, this is important for the very basics in physics and chemistry. For example, it gives rise to thermodynamics. So here you have the real gas that is not the ideal gas because there are interactions. Or you have chemical reactions which happen because there are interactions. Okay, now let's go back to classical mechanics 101 and remember what we have learned about collision physics back then. So this is the standard textbook setup, that you have a mass of particle m1 that scatters off a particle with mass m2. And then usually you do this for a Coulomb potential, and it's almost the same if you do it for a screened Coulomb, which is a little bit more realistic. And then how do you solve this? For the Coulomb potential, we can have all worked this out at some point in our lives as students or also teachers. We do a partial wave expansion to take care of the angular part. And then for the radial part, we can integrate it analytically. And when we take part, when we expand the angular part in partial waves, we get this rotational barrier that is added to the Coulomb potential. And then what you look at, or what is the quantity that you calculate, and then you want to compare with the experiment, is the differential cross-section. Right? And this is the famous Rutherford formula that you derive in classical quantum mechanics. And just to remind you what it means, the cross-section is the flow of particles, or how many particles are scattered into the solid angle element d omega. And I will discuss cross-sections in the talk, and it's exactly this, but just now that we describe the interactions of the particles quantum mechanically. Okay, so the Coulomb potential, of course, is a very specific assumption, and usually we think of point particles in classical mechanics, and already something changes when you think about shapes of colliders. So atoms and molecules are not structureless point particles. They're not necessarily even balls, so they can be dumbbells like this. And then I think it's intuitively not surprising that the interaction will depend whether the particle approaches like this or like that. So there is a dependence on this shape, and there's also dependence on the angle of the approach. So these two things give rise to anisotropy of the interaction. And so the last two slides were completely classical. So now let's look at quantum mechanics. So here's the picture I had before with these three manifestations of quantum mechanics and scattering. So apparently, I mean, this is actually an experimental paper, and this is a measured pattern in cold collision. So people can do collisions under quantum mechanical conditions or where quantum mechanics becomes relevant. And then the question is, when does this happen, or how do we get there? And the answer is, it depends on how many quantum states are populated, whether you will be able to see quantum effects or not. Because usually an experiment is done at a certain temperature, so you have a thermal ensemble, and then if you have 1,000,000 states in your, let's say, Boltzmann ensemble, like you have at room temperature or even at atmospheric chemistry, then to see coherence is very unlikely or very hard. If you go down to interstellar chemistry, then you already reach the range where quantum tunneling becomes important. And if you go down even a little bit further to, let's say, sub 1 Kelvin, then the approach of particles starts to be dominated by the long range of the interaction, which for us is very nice as theoreticians, because then we can understand very well what happens. And by now, the number of relevant quantum states has boiled down to a few. Okay? So here we have the beginning of the quantum regime. And then, of course, you can go down in temperature even further to the range of quantum degeneracy, where you have Bose-Einstein condensation or Fermi quantum gases and a single quantum state. Just to put this in perspective, so there's this nice picture back from the APS website where these temperatures are compared to the de Broglie wavelength for a cesium atom, which was one of the particles to be Bose-Einstein condensed already a long time ago. Okay, so when do we get to this quantum regime? It actually depends on the mass. So cesium, for example, is quite heavy, but also on the range of interactions. And if we now think of molecular collisions, so the first where the quantum regime was achieved were neutral alkali molecules, and then you need to go to temperatures something like microkelvin, few tens, few hundreds of microkelvin. And how people got to the molecules is they first laser-cooled atoms, and that's why you have here neutral alkalis. And then they associated the atoms into molecules one by one. And for physicists, it was very nice, and it's everything is well understood. If you talk to people in, let's say, chemistry, then they object and say, yes, but these are super artificial molecules. Who has ever heard of something like rubidium-2 or sodium-2? But still, you can do interesting experiments. And one of the pioneers in the field I want to acknowledge here is Debbie Jin, who unfortunately passed away way too young. And these were the first experiments in this field done about 15 years ago. And now there is a large number. So Martin Zwirlein at MIT, Kankwani at Harvard, Sebastian Will in Columbia University, and also in Europe you have Innsbruck and a few other places. So this is neutral alkali molecules. There's also trapping of ions and atoms, and then it's easier to have molecules because you just ionize molecules which are abundant, like, or also chemical molecules like N2. Okay, and then you co-trap them with laser-cooled atoms, and the temperatures that you need in this case is of the order of few microkelvin. And finally, there is another completely different approach that doesn't require laser cooling, which is an advantage because laser cooling is really limited. I mean, the number of things that you can laser cool is growing, but it's still limited to very specific atoms and few small molecules. Whereas the supersonic beams, so you have an adiabatic expansion, and you can do this with pretty much any molecule that you can get into the gas phase. So you suddenly, or not actually suddenly, you adiabatically increase the volume available to your gas, and that cools your molecules. So the molecules that come out of these supersonic beams are internally cold, which means they are in this sub-Kelvin regime, so not as cold as laser cooling, but cold enough to see quantum effects. And then you can, so they're internally cold, but they're moving through the lab. It's something like 1,000 meters per second, but you can manipulate them and slow them down when they have a permanent electric or magnetic dipole moment. So there are bottom lines. So these were 3 slides on more experimental techniques. I don't know how many people here are actually experimentalists, how many are theoreticians. For the theoreticians, the bottom line is there are ways to get to the quantum regime and study quantum effects in collisions. Okay, so then we can come back and ask ourselves, okay, what does this mean? So I mentioned already diffraction, and let's maybe look at this a little bit more, because I think it's nice to combine this with the intuition. It's something that usually is not done. We learn all these classical textbook examples, and then there's research on quantum collisions, but the bridge is not so easy. So let's go back to our picture of the billiard balls, right? The classical point particles that bounce off each other. So if you look at a figure like this, which on first glance seems super intuitive, once you start thinking about it, it's actually not that intuitive, right? Because the first thing that you have to realize is that these are not particles, but rather this is the depiction of the relative motion, because when you do this transformation that leads you to the Rutherford formula, that's what you do, right? And then the gray ball here is what represents the interaction potential. So, and now classically you have these bouncing off, but quantum mechanically the relative motion becomes represented by plane waves. So that's why we have the ball turns into this wave front. And then it meets this potential, and this potential acts like any obstacle. So what is unusual and what is different than from classical wave scattering is that you have diffraction into the geometrical shadow. You have diffraction patterns as from scattering from a slit. And you have diffraction oscillations as in Fraunhofer diffraction. And all of this can be measured. Okay, so now let's come to these things which maybe we associate a little bit more with quantum mechanics, namely tunneling and quantized level structure. And why does this matter in cold collisions? So as I told you, when you go to this picture that you separate the angular and the radial motion, you have this rotational barrier that is added to your potential. Okay. Now what happens is at low energies and low values of the angular momentum, this actually can become comparable to the energy with which you scatter, and then you can have tunneling. So the particles approach from far away, which is somewhere there, and then they tunnel through this barrier. And if there is a quasi-bound state, they get trapped here. And this is what's called a scattering resonance or shape resonance. And you can think of it as a natural quantization of the motion. And because then once it's trapped here, the particles, the collision complex stays there for some time, the interaction becomes stronger. And in the cross-section, you expect a peak. So these are so-called tunneling resonances, and this is not just a cartoon picture, but has been observed not so long ago, just about 15 years, for the first time in cold collisions. So here, these peaks that you see, so this is the cross-section or the reaction rate as a function of the collision energy, and these peaks here are these resonances. Mm-hmm.
Hydrogen absorbed on the surface?
No absorption. No, it's a molecular. Exactly. Two beams which are merged. Exactly. And I'll come back to that. And the specific process was panning ionization. So who has heard about panning ionization before? Nobody. One.
vacuum systems.
I'm not sure that
Measure
I'm not sure this is the same, but since I assume that it's not something that you naturally hear about, so here is what is pending ionization. You have one collision partner, let's call it A, which is in a metastable state, so it has a lot of internal energy, so much that it can ionize upon collision the collision partner, so that this becomes B and then electron is ejected. And in the what I will discuss, so A is a noble gas like helium or neon or argon, which really has a lot of internal energy. And B can be either another atom or it will be hydrogen molecules or whatever you want. And the point which is maybe for a theoretician doesn't seem so relevant, but which is actually important, is that this is because you just have to collect charged particles is very easy to detect. And one of the things that I have learned in my career as a theoretical physicist is that it's not always easy to make connection between theory and experiment, because it's not usually obvious what should be measured, or that what you predict as a theoretician can be measured. So here, having a reaction that you can see immediately is actually a huge advantage. And again, the way this is done is using this merged beam technique. So you have adiabatic expansion of, in one beam, the noble gas atoms, and in the other, the hydrogen molecules. And by adjusting the relative angle between the two, you adjust the collision energy, and this gives rise to the picture that I just showed here. Okay, so these tunneling resonances can be measured. Now, what about the internal structure that is quantized of the collision partners? Or in other words, will the molecular degrees of freedom modify the reaction rate when we do this? And we can think of, in terms of energetics, what could be relevant is rotation or is anisotropy of the potential. Okay. So anisotropy of the potential means that the potential depends on the interaction, and rotation means the molecule can rotate in space. And in order to just get an intuitive understanding whether this should be relevant or not, we can expand our potential, which depends on the distance between the particles and their angle, in terms of the completely isotropic part, and then the lowest order anisotropy, when we expand in Legendre polynomials, is this V2 term. And then there can be higher orders. So now let's ask, when we have, let's say, hydrogen molecules collide with helium atoms, do we expect that the rotational state of hydrogen can change? Okay, so then we just have to check what is the rotational constant of hydrogen. It's actually very, very large. It corresponds to about 200 K. Whereas if we look at how deep is the anisotropic part of the potential, this is just about 1 K. So the anisotropy will not be enough to change the rotational state. Clear no. But there's another way that the anisotropy can actually come into play. And here what we have to realize is we have coupled degrees of freedom. Okay, vibration or translation and the angles of rotation. And we can now use one of the standard techniques, adiabatic separation of the 2 degrees of freedom, and then treat this perturbatively. And then when we express this V2 in the unperturbed basis, we see that if we are in the rotational state 0, 0, then the interaction is completely isotropic. But in the state 1, first excited rotational state, there is an anisotropy that can come into play. And indeed, this is what has been observed in the experiment. So here are now cross-sections, again measured as collision energy. And you see, again, these resonances, peaks here and here. And the surprising part is that these two panels only differ by the rotational state of the molecule. And in one case, we have two resonances. And in the other case, there's just one resonance. So that was to us a really big surprise. So, now, first thing, how can we be sure that this is an experiment with the lowest rotational state and this with J equals 1? Well, hydrogen has this funny property that it occurs either as para or as ortho. And it's the nuclear spin symmetry that is referred to as para or ortho. But since also the total wave function of the molecule needs to obey the proper symmetry, it means that para hydrogen always has even rotational states only, and ortho hydrogen has always odd rotational states. And now, since the rotational spacing is so huge, both of them will, under even room temperature, be in their rotational ground state. But for ortho, it's J equals 1, and for para, it's J equals 0. And now in the experiment, they can actually separate para and ortho with a catalytic process, and then do the experiment with just one. So it's an easy way to select the rotational states, which is something which otherwise is quite not trivial. But here it is. And now if you remember what I told you about the perturbation theory, for J equals 0, we have only the isotropic interaction, whereas for J equals 1, we also have this anisotropy that becomes relevant. But I mean, why does the anisotropy lead to a new resonance? That's really puzzling. And so what is shown here in black are experimental results. And the first calculation we did was this green curve. And you see it's completely off. And what we do here is what's called full quantum scattering calculations, using an interaction potential that was calculated by quantum chemists using the so-called coupled cluster singles, doubles, and non-iterative triples method. This is the gold standard of quantum chemistry. And you see it fails completely. Okay, so then you can think the only mistake that you're making is in the potential. So how can we improve the potential? Well, we can add what is called the full CI correction. So that this way you treat all of the electronic correlation properly, and it starts to look better, but we still predict a resonance also here, and this doesn't fit too well. Okay, and then the remaining error is that you truncate the basis set in the quantum chemistry calculation. And if you take care of this by adding by hand only 0.4% of the correlation energy, then we get perfect agreement between theory and experiment. And just to give this a number, so the accuracy of the potential that results in the red curves here is spectroscopic, is of the order of 200 millikelvin. So there's no way quantum chemistry can calculate that. Okay, so we have a theoretical model that fits the experimental data, but can we understand what is the physics? Why do we have a resonance here but not here? This we don't see yet. And here we can go back again to this adiabatic separation of the radial motion and the rotational motion. And then we get different adiabatic potential curves for the different rotational quantum numbers. And it turns out that for para hydrogen, there exists an extremely weakly bound state. So this is not the resonance, but for ortho hydrogen, when we add the anisotropy, this state is pushed out of the potential above the dissociation threshold and becomes a resonance. And that's why there is a resonance in that case, but not in the other. Okay, so here there is no resonance state, and here there is this. So here the state is still bound, and here it has become a resonance. Okay, so far I've talked about tunneling resonances as a quantum effect in cold collisions. And here the resonance is due to this barrier through which the colliding particles can tunnel, but it's not the only type of resonance that can occur. You can also have what people call Feshbach resonances, but I think it really should be called Fano-Feshbach resonances because Fano was the one who described them first, and maybe in Italy this is particularly appreciated. So they really...
We call them.
But I think they did it more or less at the same time. The best. Anyway, what is the difference between the shape resonance and the Fano or Fano-Feshbach resonance is that here you have a single potential. So the dark blue one is what matters. Whereas for the Fano-Feshbach, you have two potentials which are coupled. So you have a closed channel and you have an open channel, and there exists a non-vanishing coupling between the two, so that when you come in on the black potential, at some point you start to feel the coupling to the red potential, and that leads to a resonance. And both provide very, very sensitive probes of the intermolecular interaction, and that's why they're not just interesting quantum effects, but also really useful tools. Okay, so now let's look how we can use this to understand reactive collisions with very strong anisotropy. And I start by first telling you about the work in the group of Canqueni at Harvard, which are the lowest reactions ever done at, I think, 50 or 100 or so nanokelvin. Nanokelvin means 10 to the minus 9 Kelvin. So really, really low energy. And what they do is they prepare KRB molecules, so alkali molecules, in their absolute ground state. So everything is in the ground state, the vibrations, the rotations, and then they let the molecules approach each other. And what happens is that there is a very deep potential where a complex is formed, and then they go out again and form from two KRB molecules, they get K2 and RB2. And the reaction proceeds, so you have some symmetry, so angular momentum is preserved and so on. And they could think of, well, which outcomes, which states after the collision are allowed. And it turns out that they have, if they count all the different quantum numbers, 57 final states, which are allowed both energetically and by symmetry. And then they measured the population of these states, all of them. And they started with something fully quantum mechanical, and they get something statistical. So the states are populated according to their statistical weight, which is like what you would also get just from classical counting, right? Which is kind of a surprise and maybe also a bit disappointing. You go to control everything in this quantum system, and you get out something statistical because your state space is too large. Okay, now we looked at a reaction with a similarly strong anisotropy, and we found, in order to explain our cross sections, again pending ionization, but now we look at the molecular products. The statistical model, which is the one that is here, the dashed dotted line in purple, completely fails. The experiment is now shown in blue, and the full quantum calculations are shown in red. And it doesn't matter whether we do this with neon or with helium. And the reason is, you may have guessed it, the Fano-Feshbach resonances. So they provide the real quantum signature of the process. So what happens? Depending ionization, we start with this metastable state here, and then the ionization you can think of as a projection of this wave packet onto one of those potential energy curves below the incoming channel. And now if we zoom in, you see that these potentials are actually strongly coupled with each other, so you can redistribute the vibrational energy. So here you have two vibrational quanta or one. You can go down to the vibrational ground state, but redistribute this into rotational energy. So it's a vibrational Fano-Feshbach resonance. And it turns out that this pending ionization process populates such resonance states. So the wave packet in orange is the result of the pending ionization, and the resonance states are the ones shown here in blue or in green. And you see that we happen to have, by luck, a very, very good overlap with the two, and therefore we get a behavior which is not statistical at all. And so here we see this resonance state with the vibrational quantum number 2, here vibrational quantum number 1, and we can explain the final cross sections in both cases. Okay, so we have again here a very, very good understanding of our theoretical model with the experimental data, but not perfect. Maybe you've seen that, okay, our red peaks, they match the blue by and large, but not everywhere. And in the end, what we're after is we want to understand the interactions. Right? So our model for the interaction is the potential. Now, can we use the experimental data to improve the potential? Okay. And here come in ideas which are very fashionable nowadays. We call them morphing, which is a way, a nonlinear coordinate transformation that you do based on the experimental data. And nowadays you would call this machine learning. Okay. So here's an algorithm. You can find the details in the paper, how we do this nonlinear coordinate transformation to modify our potentials and check if this improves. And we did this in a two-step approach. So first we said, usually the more difficult part is to capture the three-body interaction. So let's do this morphing only on the three-body part of the interaction and see how it performs. And we see an improvement. So you see the initial error are the filled symbols, and we do this for 3 different methods. And the hollow symbols are the ones after the procedure. So yes, by and large, we get an improvement. And we can then check how the potentials change. And we find that the anisotropy is changed. Well, that was sort of to be expected. But also, at least for the potential of the lowest quality, the results are completely unphysical. So if your theoretical model is too bad, and this is the standard that you would have to use for larger molecular complexes, then this machine learning ansatz doesn't really help you. It's kind of a disappointment. But then maybe just looking at the three-body part was too restrictive. Maybe you should look at all of the potential and improve it, right? So we can do that as well. And then we find that we get modifications not only of the anisotropy, but also in the long range. But what this procedure cannot do, because it doesn't have the data for it, it doesn't correct the well depth of the potential, which is also not correct. Okay, and this is in a way not surprising, because these Fano-Feshbach resonances, they're fairly extended states. They're sensitive to the long range, but not to the well depth. So you would have to repeat this with more experimental data from different types of experiments if you wanted to go further. Of course, you can also turn this around and say, okay, assume now that you have more than one potential. And for neon, it turns out there exist actually 3. Can we decide, based on the experimental data, which of the theoretical models is the best? And the answer is, well, if we take the raw data, you get these spectra that are shown here, but then there is a finite energy resolution in the experiment, and this gives us these curves. So when we include the convolution, then the difference between the potentials disappears, and we cannot really say this one is much better than the other 2. But let's assume we're theoreticians, right? We can challenge the experimentalists. How much would they need to increase their energy resolution in order to do this decision? And what is shown here is in red, the current energy resolution. In yellow, if you increase the energy resolution by a factor of 10, and in purple, if you increase it by a factor of 4. And you see with the current resolution, I mean, all these fine details of the spectrum, they get lost, but as already a factor of 4 would be enough to see that. And that's our present challenge to our experimental colleagues. Okay, so with this part, I close the part on the cold collisions. I showed you that we can probe the anisotropy of the interaction, choosing the rotational state of hydrogen. We see tunneling resonances and quantum fingerprints in reaction dynamics thanks to Fano-Feshbach resonances. And shall I stop here for questions or go on with?
Okay. Now just Koch, I understand that the simplest way of thinking is I go and find the potential and I model with the potential, but
maybe I didn't stress this enough. These potentials are ab initio potentials. Okay, so done in quantum chemistry using really state-of-the-art. I didn't explain you the abbreviations, but here we have again the coupled cluster, multi-reference CI, and then with 2 different basis sets. So this is the best that one can do, but really ab initio based. So it's not just a model potential.
no, the idea is that when you have course aligned with, you can think, look, I can have effects of a structured continuum. And is there a way to? Is there a way to?
A resonance, a scattering resonance, is nothing but structure in the continuum, and it's exactly the reason why we can see something interesting.
I know, but take the continuum, which is. So it's fine. Let's say if you would have a spectral density of the continuum, which is not flat, which is ohmic, which is super ohmic or whatever. Of course, you would have differences. Is it meaningful? Is there a way to distinguish the?
So here,
of course, you can have resonance. You can have resonances with a non-flat spectral density, which are not Fano resonances. But how is the?
So here, these are gas phase experiments. So all the interactions are already captured by the interaction potential. So when you speak of spectral density, you have an open quantum system in mind, but there is not really, I mean, this is isolated. We just having the atom and the hydrogen molecule in our description, it captures the reality. I mean, there is background gas, but no. So the structure is only due to the interaction. Merged beam.
But I mean, they must be extremely supersonic in order to cool down to temperature of the order of nanokelvin. Is it possible?
No. Okay. The merged beam you reach sub-Kelvin, but not nanokelvin. So these are products. Let me go to. So here, so this is the energy scale. So here's 1 Kelvin, and they can go down to, let's say, about 10 millikelvin, which is already pretty low, but
even go that low.
To go that low, so the trick is to use these so-called Evans-Levy valves. It's a particular valve that allows you to the nozzle. Yes. Yes. So there's a trick. Okay, then I switch in case you. Okay, let me. Nevertheless, so the experiments were actually done in the group of Edna Ravicius, back at Weizmann Institute. Now he's in Germany, and these were the students that did the experiments. And the people in my group were Carl and Daniel, who did the calculations, and we had some interaction with quantum chemists that helped us with the potential. Okay, and now I switch gear, and if you didn't find the collisions interesting, maybe the short timescales are more to your taste. And I will not talk about general ultrafast dynamics, but something very specific, and that is ultrafast ionization of chiral molecules. Okay, what are chiral molecules? Let me start with tartaric acid, which is the molecule with which this phenomenon was discovered. And for once, I prefer the German name of this molecule. Does anybody know it? It's Weinsäure. Weinsäure, so wine acid, tartaric acid. And this Pasteur, but also people, I think, before him even discovered the effect of optical rotation because these molecules have a handedness. So chirality, maybe here people still are familiar with Greek words, derives from kairos, from the Greek word of hand. And if you've ever tried to put your left hand glove on your right hand, and or vice versa, you know that this doesn't fit, or the same with your shoes. So you have handedness also in a lot of other objects, for example, snails. And interestingly, the ratio here is not 1-to-1 like with hands, but 10,000 to 1, which is good for French people because the way you eat snails needs to be adapted to the handedness. So if you would have the wrong, you could not get it out exactly. Pasta, of course, can be chiral. Most drugs, most pharmaceuticals are chiral, and this is one that was thalidomide was a big scandal in Western Germany in the 1960s because it led to birth defects all over you. So I'm from East Germany. We didn't have that, and actually, if you take ibuprofen, for example, nowadays you are guaranteed to have only S-ibuprofen in the pills that you take. There exists also the other handedness, R-ibuprofen, and in this case, it's not toxic, it just doesn't do anything. Okay. So nowadays, drugs are sold in an enantio-pure way. Sometimes, so this is carbon, another chiral molecule, and here it's funny, you can distinguish whether you have the S enantiomer or the R enantiomer just by smelling it. So one smells like caraway and the other one smells like peppermint. But being physicists, we don't want to rely on our nose, right? So we would like to know, ideally with electric fields or electromagnetic fields, whether a molecule is left-handed or right-handed. And about 15 years ago, 3 new techniques have emerged that allow us to make exactly this distinction. So one is Coulomb explosion that allows you to see the absolute configuration, left-handed or right-handed, in the lab. And the other 2 are 3-wave mixing experiments with microwaves and photoionization, where you measure a dichroism in the photoelectron. And I will focus on these 2. Because they have 2 advantages which are very unexpected. One is you only require light-matter interaction using the electric dipole approximation. Usually optical rotation, you would think, requires both electric and magnetic dipoles. But these are chiral signatures where only the electric dipole plays a role, and these are observables that can be observed for randomly oriented molecules. So in the gas phase, you have typically all orientations, and you don't need to align or orient the molecules in order to see this chiral signature. So that's a huge advantage. So what is this circular dichroism? So what happens here is you ionize molecules either with left circularly polarized light, and in this case, they used a 3-photon ionization. This is the sketch. And you measure the angular distribution of the outgoing photoelectrons. This is this figure up here. And then you do the same experiment, just with right circularly polarized light, and you measure. And even though this looks very similar, it's not identical. Okay, so you take the difference of the two and you obtain this. Something non-zero, provided the molecule that you ionized was chiral. So you observe this asymmetry only with chiral molecules. And again, this is a purely electric dipole effect, which is different from the standard like optical rotation, where you have both the electric dipole and the magnetic dipole that come into play. And you can ask yourself, how is it possible to see something chiral just with electric dipoles? Well, the point is that this optical rotation is a scalar observable, or more precisely, a pseudo-scalar observable, whereas the photoelectron angular distribution is a vector observable, because the angle defines the orientation of the photoelectron vector, the k vector. Okay, and then again, we have here the cross section, so there's some connection to the previous part of the talk. So this is now a chiral observable that is routinely measured in experiments, and it's very large because it's only electric dipole. The magnetic dipole typically is 5 orders of magnitude smaller than the electric one, so these normal dichroisms or standard dichroism experiments give you tiny signatures. The photoelectron circular dichroism is something of the order of 10–20% of the overall ionization. So can we use this for quantum control? Now, I will not really talk about the basic concepts of quantum control. If you want to hear those, come to the lecture in 2 weeks. But one is quantum pathway interference. So let's assume you ionize with 1 photon and you ionize with 2 photons. So you start from the same initial state and you end up in the same final state. Then this is like a double slit experiment, but in Hilbert space. Which means if you vary the phase between the two, you will affect the outcome from nothing at all to a maximum. So this is an idea that goes back to the 1980s. And here we used it for the ionization of chiral molecules and to enhance this effect, photoelectron circular dichroism. And we started with a gas field that uses exactly this idea of having a bichromatic field. So 1 photon with this energy and then 2 photons with half the energy. And if we use just a Gaussian shape of the 2 photons, we get an effect, but it is comparatively small, 4%. And if we analyze the contributions to the final signal from the 1 photon and the 2 photon ionization, you see here the different sign of the peak. So the interference is actually destructive. And we can use optimization techniques, quantum control, and align the phases of these 2 components in the field. And we see that now the interference becomes constructive and the numbers go up to something like 20%. But then we don't have to have frequency components in our electric field that are exactly twice that of the other. We can freely optimize the field. And then we can drive these numbers up to almost 70%.
Sorry, I did not get if the interferences between the two photon paths.
I will get to it in just a minute. Exactly, because now the question is why is that? So here is what happens in this real molecule. So we have electronically excited states. These are the lines here. And we can drive these 6 different pathways, essentially. And if all of these frequency components overlap, we get the maximum. If the low frequency part of the optimized field and the high frequency part are time delayed, such that, let's say, only so in the red case, the low frequency photon comes first and the high frequency photons comes later, then we have no interference because they all probe the same intermediate state. So here we have a constant. Whereas if we first come with the high frequency part, okay, we have these 3 different intermediate states that can be populated, and then they're ionized all to the same final state within the bandwidth of the pulse. So that's why now we have interference between these pathways, and we see these oscillations that between constructive and destructive interference in the signal. And when the two overlap, then we get this maximum contribution. So this is our suggestion of doing sort of standard coherent control on this chiral observable, which is
The intermediate are virtual state.
they're electronically excited states of the molecule. Excited states. So they're not virtual. They're
Because usually
yeah. So these are resonant.
these are
Yeah.
But the intermediate are not populated.
Not really, because everything is happening on the timescale of
They are built.
50 or 100 femtoseconds. Yes. Okay. So when I showed these results to my experimental collaborators, they liked it because it's this old idea of coherent control. And then they looked at the pulse and they said, at these photon energies, quite high, pulse shaping techniques are not really very well developed. Now in Trieste at the Fermi, they start to be able to do it, but is not really yet there. So then, can we do something about it? And it turns out we can. What we do here, okay, is we have two photon pathways that we interfere. So these are 6 different 2-photon pathways. Now we can create 2-photon pathways also using a technique from the attosecond community. So maybe you heard about attoseconds with a Nobel Prize in 2023. One way to get them is to have these frequency combs. So you have an XUV comb with these purple lines. And now you add to this attosecond pulse an infrared laser. These are the red lines here. And then you see, to get, for example, to this final state, you have 2 ways. You can go with omega-9 and the infrared photon, or you can go with omega-11 and minus the infrared photon. So these are also two 2-photon pathways which interfere at the sideband that we labeled 10. So that's a standard technique that in the attosecond community is routinely used. And now we apply this to this chiral observable photoelectron circular dichroism. And we see that indeed we get a signal at these sidebands. And now we can even vary whether we have, let's say, circular polarization only in the XUV comb or both in the XUV field and in the infrared field. And if we have both circular polarizations, then we get a larger signal. The advantage of this is, so these fields already exist in the lab, and it's a very robust way to probe the chirality. And maybe I don't go into technical details. If somebody wants, I can explain. But actually, what we predict here has, in the meantime, been observed in experiments by Hans-Jakob Werner in Zurich. Okay, one thing that I like about this is that we can, by changing the polarization for either the XUV or the infrared, we can probe which part of the chirality comes from the bound part of the spectrum of the molecule and which from the continuum. Because the XUV starts from the ground state. So this is the ground state chirality. And then in the continuum where the IR acts, we only have linear polarization. Okay, and here it's the other way around. So here only the IR, which acts on the continuum states, is circularly polarized. So here we probe the chirality only of the continuum states. And you see that the numbers are quite different, which is not so surprising. What is maybe surprising is that there is any chirality in the continuum states at all. Because how I have to think about it, the chirality is the molecular scaffold, right? So the nuclei have a handed configuration. And now I'm ionizing my electron, so it flies away. And it flies away, so it leaves this chiral environment. But yet, there is some trace of it, so it still feels this chiral potential from the nuclei, even in the continuum. Okay, So this we have now this observable, which is readily available, and we can play the games of quantum control with it. Now, let me tell you one more thing which I found, or which I find fascinating. And that is, so there are a completely different type of experiments, and I will not bore you with the details, but it uses microwave radiation and rotational dynamics. And here we have seen its laser fields or XUV fields, so spectrally a completely different region. And here we have rotational spectroscopy. Here we ionize, so also the physics looks quite different, right? Rotational versus electronic. Yet, you can, if you look at the expressions for the observable that is measured, so this would be for the photoelectron circular dichroism, it has this structure of a triple product. And also in the microwave case, you find this triple product. And it turns out, which is what has been found in this paper, that it is this structure of the vector triple product that gives rise to a non-zero chiral observable, even for randomly oriented molecules. So when you average over all the angles for the molecules. And this is an insight that we have used, and this is the final point of the talk, to answer this question. Can we make a molecule which originally is not chiral? Can we make it chiral and probe the chirality? And this question actually is not so interesting, but what is really interesting is, can we make an ensemble of molecules chiral and probe the net chirality of this ensemble? And the answer is yes, with a vector observable that obeys this vector triple product structure. So how does this go? Let's be a bit more intuitive. So the idea is we induce chiral dynamics. So we start with a planar molecule, and here's one that we found. So all the nuclei lie in one plane. And now we excite the out of plane vibration, so of this, essentially of this carbon atom. So when it's above, let's say it's right-handed, when it's below, it's left-handed. And we can do this just by the simplest superposition of vibrational states, let's say 0 and 1. So we have our beloved two-level system. And now, if you're a molecular physicist or a physical chemist, if you want to create such a superposition, usually you would do this with an infrared laser, excite vibrations. But if you do this with an infrared laser, then for a single molecule, it's okay. But if you have an ensemble of molecules, half of them will start to vibrate like this, and the other half will start with a phase delay of pi. So the net chirality will be 0. But here's the lesson. If we are able to get this triple product, then we can define the handedness. So how do we do that? Well, we use a Raman transition with circularly polarized light. So this gives us 2 of the vectors. And then we need a third vector to build the product, and we use a static electric field. So here's this more formally. We have to integrate over all the molecular angles, and we need to make sure that this expression is non-zero. So with the Raman excitation, which is these purple arrows here, in the presence of a static electric field, we get exactly the triple product that we need. And indeed, now we can, so the idea is we do a pump probe experiment. The pump is this combination of Raman and static electric field. And then after a time delay, we ionize and we measure this photoelectron circular dichroism. And you see here how the chirality changes from left-handed to right-handed, and the different curves here correspond to different angles at which you measure. Here's the setup that we envision. So we have this static electric field, which is created by these coils, and then the Raman pulses and the probe pulse, and do this chiral pump probe experiment. And this could be used, for example, to measure parity violation, which is one of the things that chiral molecules would be good for. Okay, for this, I'm at the end of my talk. Let me really be very brief in my summary. I told you about quantum resonances in cold collisions as a super sensitive probe of intermolecular interactions, and quantum control of chiral molecules, where we exploit quantum pathway interference. And if you want to hear more about quantum control, come to the lectures, and these will be on quantum technologies. And for today, I thank you for your attention.